Hey guys, so a lot of our next investigation is going to focus on perfect squares, those numbers that are very special numbers, and we're looking at the multiplication table right now, just the positive part. But these are the very special numbers that are a square of a whole number. So this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc. And for example, 25, you can see it's 5 squared because we're multiplying 5 times 5. So we're really going to be focusing a lot today around the patterns that you'll notice if we focus and hone in on one single perfect square number. So for example, if I start with the number 36, so this one right here is in our table the center. Okay, ours only goes up to 12 squared, but of course you could extend this forever. We're going to kind of take a look at the numbers almost like in like a ring, except for it's a square surrounding it. And you can see that if we go one away in either direction here, there's 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different numbers that surround it. And we're going to play around and look for patterns in these numbers. Okay, so let's go ahead and move on to the worksheet that I gave you guys, and we'll work through a lot of this together. All right, so on my screen you can't quite see all the directions, but you have the instructions for this uploaded for yourself. So here's another recreation of that situation, and we said to put 36 in the center, and I'm going to use a different color for this. So 36, and fill out the other numbers surrounding it. So you just want to look at your multiplication table and just fill out those numbers. And our goal here in the end, I just want you to know, is eventually going to be, if I start with a different number here in the center, can I actually predict what's going to be in the other ones without looking at the multiplication table because I've found some patterns? So we asked, put 36 in the center and fill out the numbers, and then write in words how each of the surrounding numbers relate to the center number. So this is one where I'll just let you do this on your own right now, and you can pause the video, and then we'll come back together and we'll look at it with each other. Okay, so I'm assuming you paused and you filled it out. Now filling it out obviously is easy because at this point you're just looking at the multiplication table actually. So if you go down here, it's 30. Whoops, I wrote the wrong number, 30. And then up here is 42. And then here is 35. And here is 35. And here is 42. And then 30 again. And then we have 25 here and 49 there. And again, we're trying to describe in words how the numbers relate to the center number, right? So I might just write them along the edge here. We don't need to use tons of words, but you're probably going to be thinking more like adding, subtracting relationships right now, which is totally okay, because we've learned in the multiplication table, actually, we've already learned the up and down and the left and right. So those are pretty easy. We can just say this has gone down 6, and this one here has gone up 6. And in fact, we can see that the right and up have the same effect. And then if we go left versus down, they also have the same effect. So these are both up 6 and down 6. Now we go the diagonal directions, which are a little bit weirder. You'll notice something really interesting here is this goes to 35, but so does that. And you may just choose to say that it's gone down 1. There's other ways, but we'll look at that as we go on. That one's gone down 1. Now these are tricky. You may just say it's gone up by a certain amount or down by a certain amount. That's totally not wrong. Another thing to notice is that if we look along here, in fact, I'm going to mark it out with another color just because this is the diagonal that we were looking at in the first place of perfect squares. So you may just think, oh, well, this is 6 squared, and so this is 5 squared. And then this up here is 7 squared. So this is like um, the next number down squared. It's hard to say, you know what I mean? Um, but it's okay with me if you just leave it as 5 squared and 7 squared. Okay, but either way, just realizing these are the perfect squares on the diagonal, and this goes 5 squared, 6 squared, 7 squared. But then from the center here, these just go up and down. Now you'll notice this 6 is really important, okay? Because 6 squared was 36. And so that location of 6, that probably feeds into some of this. So here's what I want you to do for the remainder of this for now, is your job is to repeat for another perfect square of your choice from the multiplication table. Now you do not have to do this in words, that's okay. But what I want you to do is choose another perfect square and put it in the center here, and then do it again here. And then see if you can predict what's going to go in the surrounding locations without actually looking at the multiplication table. And then you can, of course, check your work. I'm not going to do these myself because I just want to see that you chose your own and that you did it on your own. And then we're going to continue on now and take a look at some other patterns as well. So now that you've looked through one, you've kind of tried to keep your eye out for patterns. This is almost like a quiz for yourself. Kind of the last ones sort of were too, but I said to place 225 in the center. And I reminded you 225 is actually 15 squared. And you'll notice that this is not actually already in the multiplication table that I gave you. Now, of course, you could certainly fill out the multiplication table further and extend it on as far as you want. But again, we're trying to do, algebra here, which really involves looking out for patterns. And so see if you can predict what's going to go in the rest of this on your own now. You were able to check your work for the other ones you chose, but for this one we don't have a way to check our work. But go ahead and do this on your own, and then we'll come together and you can see if you're correct. Okay, well, let's take a look at this and we can check our work. Now, hopefully you realize that this is going to be 14 squared and this is going to be 16 squared because these are still going to be along that diagonal that goes this direction. And so whatever those numbers are, 14 squared and 15 squared, which that's something that I know my perfect squares pretty well, but I always forget 14 squared. Oh yeah, because it's right after 13 squared. It has a pattern. So this is 196, see if you got that right. And then 16 squared, and again, it's okay if you use your calculator, is 256. And then how about this other diagonal? Hopefully you recognize for all of these, they actually just go down by 1. So 224, it happens to be on either side on that diagonal. That's weird how this diagonal has this is the peak in the middle, and then it goes down. And same in the other direction, it goes down. So this is like the largest one if we're looking at that diagonal. Whereas this diagonal, it keeps increasing, and each one is the next perfect square. Now hopefully you realize since 15 is an important number here, and actually that number 15 is what we go up and down by if we're looking vertically or horizontally. So 225 minus 15 is going to be 210, and plus 15 is going to be 240. So go ahead and check that you got that. And these happen to be the same, so we can just do 210 and 240. So it's pretty cool. There's a lot of patterns that exist in numbers just simply by looking at the multiplication table. And we are, of course, specifically focusing on the perfect square patterns. Now we're going to do something a little bit crazier. Let's look at number 3. It says, I want you to study one more ring out from each perfect square number higher than 12. Now I'm going to ask that you do one higher than 12, but actually what I want you to do first is you can go, I'll go ahead back here myself into the original multiplication table for a minute. And let's look at that 36 again. So what we're saying is let's go to the next ring out, but we're not gonna do all the numbers in the next range. So we're gonna actually we're gonna just go out in the same directions we went in the first round. So we're still looking at the 8 numbers that like just continue to extend. Maybe this is hard to see. So, we're looking here, 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 etc. Okay, so we're actually just looking at these numbers here for now. Not that there aren't other patterns, but it gets complicated quick, so we're going to stick to these. Now let's see if you can study those numbers and what you think is happening there. So you have our 36 in the center, and then it goes 35, but then it goes 32, but then this one goes 35 and 32 as well. You might actually kind of look out for some patterns there. And then here, well, you might see the same pattern because it's still just the perfect square thing. So if that's 6 squared, then that's 5 squared, and that's 4 squared, and that would be 7 squared and 8 squared. But then you can think about the up and down part too. So we're just predicting even further beyond just the one ring, I guess we would say. Okay, so I want you to pick your own number. I'm going to do one with you guys, but that's not the one you should write down. I want you to write down your own number, higher than 12 and other than 15, because we kind of did 15 already, and use its square in the center. So if you chose 13, then you'd put 13 squared here, but choose your own number, and then see if you can use the patterns in the multiplication table to write the prediction of what it would be. Okay? So let's go ahead and actually test one together. I'll do 13 squared since I already mentioned that, which is 169 if you were to multiply that out, okay? And this is 13 squared. Well, you'd probably realize this is 12 squared and this is 11 squared, and 14 squared and 15 squared are up here, okay? And if you multiply those out, we'll write what we get here. Okay, so you realize that, and then hopefully you realize from your studying that this just drops, we already saw this drops by 1, so we'll write 168. And then hopefully you realize that always, if you go down 2, it drops by how much? 4. So this becomes 165. That's interesting. And this becomes 165. And here, 169, since this is 13 squared, you'll notice the up and down thing is exactly the same as it was before. We're actually just dropping by 13 and 13, or whatever this number was for you. So 169 minus 13 is 156, and then 143, which is going to be the same here. And then if we add by 13, we're going to get, I think it's going to be 182, and then 195. 182 and 195. Okay, so anyway, again, we're just looking out for patterns. So to recap this, if we're going on this diagonal, these first outer ones go down by 1, but then the next ones go down by 4. And in fact, you can look yourself real quick. If we go even to the third one on this diagonal here, how much does that go down by? This went 1, 4. Go ahead and look. That one goes down by 9, actually, and the next one also by 9. And then after that is 16. So if you think about 1, 4, 9, 16, it's interesting. This is going up and going down, and in both directions we're going down, and we're going down by the successive perfect squares as you go down. That's really weird. And then this is still having the same exact pattern. Since this is 13 squared, then this is going down by 13s and up by 13s, and the same things happen here. And then these are just the perfect squares still. It's just the next perfect square up or the next perfect square down. Said, we're going to explore the patterns we're noticing, but with variables, and we'll do this together. There are a lot of interesting patterns and things for us to see here, but also some important identities. And since we're going to move into our next investigation studying some of these identities, then that's why we are going to spend some time with this now. So here's what we're going to do. In the very center, go ahead and place with me x squared there. So what we're saying is, here's the position, and remember my multiplication table is, we have our x and our y axes that exist out here somewhere. And so this would be at the position, and let me actually scoot my paper over a little bit. Okay, wherever those x and y axes would be on your multiplication table. I didn't do a great job. Let me make these so they're actually kind of similar distance away from each other, okay? Then on here, this would be x. And then if we go out here, this would be x plus 1. This here would be x plus 2. This would be x minus 1 and x minus 2, if that makes sense. But then up here on the y-axis, here would be my x. Here would be x minus 1, x minus 2, and then of course, eventually this becomes 0, but we're at a variable place, so, and then, okay, so just keep in mind those specific locations there, and that's something you can also draw in that's going to be important. Now, based on the patterns we've noticed, let's actually just fill in this whole thing. Now, you can pause and take a stab at this yourself if you think you're comfortable with it. It would be a really good exercise. If you don't think so, you can just go through with me. But either way, it's really important that you're focusing on trying to understand why this is the way it is, please. Okay? Now, you'll notice something here. This is always going to be this number minus whatever position we're in. So we're in the position of x, right? So this is x squared minus x. Does that make sense to you guys? Whereas up here, we're going up x. So it's going to be x squared plus x. But then I have to go down another x here. So we still have our central point, which is x squared, but we're going down another x. So if I've gone down x and down another x, it's going to be x squared minus 2x. And therefore, this one's going to be x squared plus 2x. And the good thing is, we can actually see this is going to be the same. So let's just write it in here. Plus x squared plus 2x, x squared minus x, and x squared minus 2x. And then you probably also realize this diagonal, well, it doesn't matter which one we put, but this diagonal here is simply going down 1, but then down 4, and then repeating up there. So we could just say x squared minus 1 and x squared minus 4. Does that make sense? And this is also x squared minus 1 and x squared minus 4. And then we have one last diagonal. This one's a little trickier maybe to think about, but if this one's not going to be directly changing something with x squared. That's what makes this diagonal a little bit trickier. Now you might actually find some patterns yourself that are very interesting for how they work. I've had some students pull this out on their own, but I think the easiest way to think about this is, if this was x squared, this was the next number up than x, but then squared, right? Well, what's the next number higher than x? Isn't it x plus 1, right? But it's the square of that. So I'm going to put parentheses around it, and the whole thing is squared. So for example, if x was 15 like we did, this is 15 squared, and this was 16 squared. So that's why we had the parentheses here, because 15 plus 1 gives us 16 squared. Now I think you could probably fill the rest of these out yourself, now that we've done this one together. And you could also, again, you could pause and do that yourself real quick, or do it ahead of me real quick. Now we'll check. So this one's going to be one more than that one, so x plus 2 and the square of that. But this one's going backwards, so instead of x plus 1 squared, it's going to be the square of x minus 1, and then the square of x minus 2. Now actually, if you think about it, it might have been a little harder to figure out how to write the ones on these diagonal here, the perfect squares. But if you actually look back at the axes and you remember how the multiplication table was made, remember that any number in the multiplication table came from multiplying the column you're in by the row you're in. So right here we're in row X, and this is column X, and this is row X. So X times X is where this came from. X times X is X squared, right? And so it should also work out that we should get that in any other one of the rows and columns. So look at this. This is X minus 1, and where does it meet here? X minus 1. Well, what's X minus 1 times X minus 1? Oh, we can say that that's X minus 1 squared, because it is. It's times himself. And same here, X minus 2 squared, X plus 1 squared, X plus 2 squared. And how about all these other ones? They should be able to be constructed in that same way. Let's actually look at a couple of these together to wrap up today, and that will be what we finish off on. So for example, let's just take a look at this one right here. This is X squared plus X, right? So I'm going to write this down here. X squared plus X, but I want you to notice something. The column it's in is X plus 1. And the row it's in is X. So we know that X plus 1 times X should create whatever's there. The cool thing is we actually thought of that in a slightly different way. We didn't think of it as taking X and multiplying it by the next number up. We thought of it as taking X squared and then just adding X to it. But we all have learned this already. X times X plus 1 is actually the same, right? We've learned the distribution property as X squared plus X. But if you actually think about the numbers, like if we use 6 again, right? 6 squared plus 6 is 36 plus 6, which is 42. But we could also think of it as 6 times 6 plus 1, which is 6 times 7, and that's still 42. So you'll notice that a whole way these are equal. This is an identity, and we actually constructed it in slightly different of a way. So our patterns we looked at just simply by going out away from the center number made me think of it as X squared plus X. But based on how we know the multiplication table works, we can also think of it as X plus 1 times X. So a lot of identities we're already familiar with, and maybe even ones we aren't familiar with, can be found out from thinking of these in this way. And you'll notice all these have that same kind of thing. Like, let's look at this one right here. This one's X squared minus 2X. And notice that he came from X minus 2 times X. And you and I both know that X minus 2 times X, or X times X minus 2, if we use distribution, becomes X squared minus 2X. So it's pretty cool how the multiplication table helps us see a bunch of these identities and things. Here's another cool one, and we're going to end with this one as our final identity. This last one here, in fact, it's going to be so related to what we're doing that I'm going to do it in a different color. X squared minus 4 came from X plus 2 times this same one we just used in the other one, X minus 2. So X minus 2 times X plus 2 is equal to X squared minus 4. So we actually could have put in here X plus 2 times X minus 2 if we wanted to. But based on the patterns that we noticed before, we saw that it's equal to X squared minus 4. The cool thing about that is we've already kind of worked on multiplying polynomials. X plus 2 times X minus 2, if we actually work it out, becomes X squared plus 2X minus 2X, and then minus 4. And you'll notice that this plus 2x and minus 2x cancel out, and this just becomes x squared minus 4. And that's exactly what we suspected there. So, I hope you enjoyed this lesson, and happy math. We will see you next time.